Hello to everyone that decided to connect with my presentation, and thank you very much. My name is Davide Poggiali. I'm a postdoc at the Padova Neuroscience Center, and this is an MRI of my own brain. I ended my master degree in mathematics and after a PhD in neuroscience, and I'm going to present you a work about fake nodes approximation for magnetic particle imaging. This is a joint work with Stefano De Marchi, Wolfgang Erb, Francesco Marchetti, all from the University of Padova, Elisa Francomano from the University of Palermo, and Emma Peracchione from the University of Genova in Italy. This is the summary of my talk. I will introduce the reconstruction problem in MPI, magnetic particle imaging. We'll introduce as well the fake nodes interpolation method, some numerical experiments about MPI reconstruction, the results, and future works. These slides that you are watching are available online at this address, and if you're interested in some other work of mine, just connect to my website. Magnetic particle image, or MPI from now on, is a tracer-based tomographic technique of recent development. It has been developed in the zeros of the 2000s. Now, MPI system detect the spatial distribution of a tracer, which is super magnetic nanoparticle, which is injected in the body. How does it do it? In a nutshell, image acquisition in MPI it's performed by generating a magnetic field free point, which is an eye of the storm, moving along a chosen curve, which we're gonna call gamma of t, and then inducing a measurable voltage signal in a receive coil. So what we are doing to acquire image in MPI is simply to generate a point in which the only electromagnetic contribution is given by the tracer itself. Now we obtain a scatter data and we can simply interpolate it over a regular grid to get a human readable image. And from now on we will refer to this interpolation process as reconstruction. So reconstruction is an interpolation from the scattered data we obtain in MPI and a regular grid, a simple image that you can read in everyday life. Now, a commonly used trajectory in MPI are, for instance, the Lissajous curve, which is those gamma of t, which are two cosines of different integer frequencies. And the sampling points on these curves are the so-called Lissajous nodes, that are these ones. So this is a 2 pi periodical curve, so it's a closed curve. And if we sample this number, we take this number of samples, which are 2 epsilon and 1 and 2, we get a sampling of this curve over some nodes that are not at random. Now, just to make it clear, I made a GIF. The sampling points are the intersection, the self-intersection of the curve, and the intersection with the curve and the boundaries of the domain -1, 1 squared. So this is how we get the signal. We have this field-free point in black, and the receive coil are getting samples at very specified nodes which are the Lissajous nodes. So what we obtain is our signal in this grid, which is scattered, and we want to reconstruct it over an equispace grid. So what we need is an interpolation method. Now, let me introduce the fake nodes interpolation family of methods. Interpolation on fake nodes or via mapped bases is a technique that applies to any interpolation method in any possible dimension. It has shown in many cases the ability of obtaining a better interpolation, more precise or more stable, without getting new samples. This means that provided that the original nodes are a sufficient sample of the signal, it can be possible in principle to provide a more stable or accurate interpolation. So in terms of code, what are fake nodes? What is fake nodes interpolation? Suppose you have a generic interpolation function that can be in 1D simply polyfill and polyval, just to make an example. Now, instead of calling the function directly, as in this 1D example, you just define a mapping function S, which is a choice of yours, and interpolate over the fake nodes S of X, and evaluate over the sampled evaluation node. So you apply a sampling over both the interpolation and evaluation nodes, and this maps gives you some extra powers over the interpolation. Now, this is the generic interpolation method. Suppose you have a function of over Rd, over a subset, defined over a subset over D, which D is a dimension, whatever it is, and a set of distinct nodes over interpolation. Suppose you also have a basis of functions. Now, the interpolant is given by a function like this, such that it passes exactly to the nodes. Or in case of least squares approximation, the two-norm error is minimized between these and these. Now, the fake nodes interpolation is simply this one. Suppose you have a set of bases, which are the original bases composed by S, and now the interpolant is given by this function, and it's such that it passes to the nodes, which is the interpolation condition, or near the nodes in least squares approximation. Now, we have a set of simulated MPI data whose ground truth is known. So we have a simulated data with these three parameters for the curve, and we want to reconstruct over a 2001 by 201 by 201 X-spaced grid and test different interpolation methods. Now our results will be compared to the ground truth. Different interpolation methods have been used. For the first one, the bivariate polynomial interpolation of total degree, which is x1 to the e, x2 to the j, such that the sum of e and j is smaller or equal than the degree. And for that one, we use the least square approximation with k21. We use as well RBF interpolation. Now we have a basis of kernels where the k's are a radial basis function, which is a function defined over the two norm of x minus xy, given x with a, the interpolation points, and we choose the matron function of different regularities. Now this is the C0, the C2, the C4, and the C6 continuous functions, respectively. Now, how to choose the mapping S? Since our signal is discontinuous, the reconstruction will be affected by Gibbs phenomenon. Gibbs phenomenon is simply some non-physical oscillation around the discontinuity, which always happens when the signal is discontinuous. Now, to prevent this, we used fake nodes interpolation with the mapping S choose like this, being the gamma of k, the non-overlapping set given by a segmentation of the image. So we made a segmentation of our image based on the data we have, and we simply moved the sampling points in a way that they do not overlap and that different areas of the segmentation are distant one from the other. So this is the original samples colored with the intensity of the signal, just to be clear, and this is the effect of the mapping in the interpolation points. So what we see is that the two stripes here have been displaced by our mapping S. Now, how to performance show a comparison of performances. We used, for instance, the symmetrized Kullback-Leibniz divergence, where this is simply defined like this. This is a mean of those objects, and we choose the symmetrized version. So this is a real distance and not only a semi-distance. So Sk of L of Ai is simply the symmetric sum of the two. This is an operator which is defined for image especially, and to compare two images one to the other, but not only for this purpose. Let me show some results. On the left we have the polynomial approximation, which is kind of blurry, and the polynomial plus fake nodes approximation. As you see, our segmentation gives us the possibility to better reconstruct the difference between the stripes and the fundus. This is the C0, so the Matern C0 interpolation with RBF. So this is the pure RBF interpolation, and on the right you can see the fake RBF interpolation, where once again our stripes are better delineated and we better see the difference between the stripes and the fundus. Let me show you some results in terms of SKL. Now, as you can observe, in most of cases, the fake version of each interpolation method leads to a better approximation of the ground truth, especially in case of polynomials. Here the difference is like very huge, it's huge with respect to the other. And another observation that we can make is that choosing more regular RBF basis, Matern basis, does not lead to a better approximation, which is kind of strange for those who are used to regular signal approximation. But our signal is irregular, so it privileges less regularity than more regularity. The future works consist in testing other RBF function and with different shape parameters. In our presentation and work, we have fixed epsilon equal to 1 as shape parameter of RBF, trying as well moving least squares approximation method, and we are planning on using fake nodes to other biomedical application as well as image denoising, resolution approximation of an imaging system, and reconstruction on MAG-AG. Thank you for your attention and your patience as well. And below there are listed some of the references that this work is based on. Thank you again for all your attention.